Good morning. Welcome to the monthly Launchpad lecture. Obviously, I am not Chris Orwell. He sends his regrets. Family issue came up and we won't be able to make it today. So at the last moment, he asked one of us to stand in, and I was crazy enough to step up. Yes. So today we're going to talk about the James Webb Space Telescope instead of Apollo 15, which Chris may do at a later date. So the biggest telescope ever put into orbit, put into space. Not the biggest compared to those that we have on Earth, but it is simply going to do phenomenal stuff. A little bit of the background on it. It's named after James Webb, who is best known as the NASA administrator who got the Apollo program, the manned space program, Mercury, Gemini, and Apollo, on a good solid footing, good management footing, so that everything worked out as well as it did. But in addition, and this is the reason they named it after him, he made sure that NASA was engaged in vigorous long-term space science projects. So they named the telescope after him to honor that. And it is an international project. Memorize the list, will be a quiz at the end of the talk. It's largely a U.S. project, most expensive one, probably short of Apollo or space station. $9.7 billion, significant delays and cost overruns, but I think it's going to be well worth it in the long run. In addition to the U.S., the European Space Agency and the Canadian Space Agency have made significant contributions. The Europeans in particular are launching it on their Ariane 5 out of Kourou, French Guiana. That gives you an overview of what it looks like now that it is fully deployed in Earth orbit. In orbit trailing along with Earth at what is known as the L2 position, libration point. We'll talk about that in a little bit. It's an unusual design. You might wonder, why is the telescope open and completely exposed? And actually it's not. You think about the telescopes you may have seen at star parties and quite often in images, photographs of observatories, and the tubes are really to reduce stray light. And we've done that on Webb, both by combination of the sun shield and positioning it far past the moon. We'll get to that in a little bit. It's highly reflective, and a lot of what keeps it cool, which we need to do since we can look down in infrared, down to heat radiation, a lot of the cooling is simply with those blankets, which are basically the same as the astronaut-type survival blankets you could buy in the gift shop or at a camping supply store. But getting this unfolded was the stuff of nightmares. I'm sure that a lot of people lost many, many nights of sleep worrying whether the rocket would get it off the ground, whether the parts would unfold the way they were supposed to, especially after they ripped one of the blankets during a deployment test on the ground. And that put them back really over 3 years between that and other issues that they discovered with it. So Tony and I were discussing it. Neither one of us would have bet a nickel that the whole thing has worked out the way it has. It's just nothing short of miraculous. This gives you an idea of the overall size of the primary mirror. The sun shield is not even deployed because it's not possible to do it in this particular test. This is in the thermal vacuum test chamber at Johnson Space Center that was built originally to do thermal vac tests on the Apollo spacecraft in the 1960s. So you can see the team back there in the clean room bunny suits. That gives you an idea of the size of this thing, 21 feet in diameter, and it had to fold up in order to fit within the Ariane rocket. And it's probably the last time we'll do something on that order of this kind of complexity, because larger launch vehicles are coming along, robotic assembly technologies, but in the meantime, let's just enjoy what we've got with Webb. So here it is, primary mirror compared with the primary on the Hubble Space Telescope. And in both cases, the center of the primary there on Hubble is empty. The center hexagon on Webb is blank also, because that's where the light goes through to the instruments. Here's another way of looking at what a leap it was. It's difficult, quite often, to do comparisons between visible light astronomy, which is what we think of a lot, especially if you go to star parties, and infrared or ultraviolet X-ray, because different subtleties in optics are used. That is just one of the 18 mirror segments for Webb. Over there on the right is the Spitzer Space Telescope, named after Lyman Spitzer, who helped make the Hubble Space Telescope happen. That's the entire telescope array. The primary is only about 2/3 the size of one segment for Webb. And the secondary is in the little dark gray cylinder up at the top of that cylinder. And Spitzer did remarkable stuff, and I'll show you a picture in a minute that'll tell you just how remarkable Webb is going to be. This is the combination fine guidance system and near-infrared imaging slitless spectrometer. Okay, remember that, will be on the test also. But I put this in here to show the complexity, in addition, of the science instruments. These things by themselves are bigger and more complex than a lot of the small astronomy satellites that we're launching now. This one was provided by the Canadians. This thing to there we go. Okay, so the science instruments sit in the black doghouse that is just behind the primary mirror. And you might think, well, why would you paint it if you want to operate at really cool temperatures? Why would you make this thing black? Because it absorbs light. Yes, that's true. But first off, that's in the shade. Secondly, black is also very, very good at emitting infrared radiation, which is why, for example, space shuttle heat shield tiles were painted black on the belly, because those were exposed to the most severe heating during re-entry. Okay, big picture, so it's a little bit slow today. Come on. There we go. So launched Christmas Day last year with an Ariane 5 rocket, liquid propellant core, 2 solid boosters, and we had video on board the second stage. I think my computer needs a little bit of coffee this morning. We had computers on board the second stage, so we got one last look at it as it was coasting away. Had been boosted into its almost interplanetary trajectory, and will spend the next month coasting out to the L2 vibration point. And one of the discussions we were having earlier is that the thing cannot be serviced. Actually, it might be possible. It was not can't be serviced the way Hubble was, with astronauts going up and wrestling instruments in and out. But the key thing that limits its life is how much fuel is on board to help keep it on station. It was designed for 10 years. The Ariane rocket did such a good job that they have extra propellant left on board so they can make it 20 years. And then NASA included just the right bit of grapples and some optical tracking and everything, so that maybe in another decade or so, a robotic spacecraft could go up and refuel it, keep it operating. Okay, vibration point, what the heck is that? There are 5 of them. They're gravitational balance points, if you will, between Earth and Sun, or on a smaller scale between Earth and Moon. The L1 point is in the opposite direction, towards the Sun. We have a number of solar observing satellites located there. L2 has been very good for positioning spacecraft that need to be very cold and observe deep space, studying things like the cosmic microwave background. The Europeans put the Herschel Space Observatory there as well. So you're far away from Earth, and you can have all the reflected light from the Moon, infrared radiation mostly from the Earth, because you're always going to be on the night side, and the Sun behind you, and you can have that open telescope design. So it was a long coast to get out there. I get my slide to come up.
Dave, you got a question?
Yes.
Can you put more than one in that L2 position?
Yes, space is, as the Hitchhiker's Guide to the Galaxy says, space is big. It's unimaginably big. You wouldn't believe how huge, blah, blah. Yes, there's plenty of room. The spacecraft are tiny, and if you can envision super tankers and big cargo.
You could put a whole colony on the L2.
Actually, that has been discussed, would be to have colonies at the L4 and L5 vibration points between Earth and Moon. Jerry O'Neill started popularizing that concept in the 1970s. Okay, so the journey to L2, coasted out, and then use the onboard thrusters to burn for several minutes and put it into this orbit. They're not positioned directly right spot on at L2, sort of orbiting it. And the neat thing is, so with that sunshade, the telescope can't look everywhere in the sky. It doesn't have to, because as you orbit Earth orbits the sun and you're trailing along with it, that circular region, field of regard, where you can point is going to change as you go along. So every 6 months you'll be able to access every single point in the sky. So on the way out, now that we've got the spacecraft, the Webb launched, really like, there we go. We started unfolding it. So the first part is the pallets holding fore and aft portions of the solar, of the sun shields deployed. And then the really difficult part, extension booms gradually punched outward to expand it. Then the next difficult part, the thing has 5 layers, so it's gradually tensioned and raised so that it separates. No one sunshade can block all the sunlight, but 5 of them together, they'll reflect most of it out, and the gaps are set so that light that does penetrate should bounce and eventually leave through those gaps. Plus, you don't want to have everything relying on just one sunshade, because if it gets hit by micrometeoroid, which it will eventually, it's big, it's going to be out there for decades, you don't want that one pinhole focusing light on a place that needs to be kept incredibly cold. Now you got sunlight coming through. So you got it deployed, everything tensioned out, no webcams on board. People ask them, why didn't you put webcams so you can see it could be deployed? And they said, didn't have to, because, well, A, that would have been a layer of complexity they didn't want to mess with. B, they knew the responses from the motors and the instruments so well, and the accelerometers on board, that they could tell when things have been moved back and forth. And the one real hang-up they had was one sensor indicated that part of the sunshade had not deployed properly off to the side. But they looked at the accelerometer data and they could see, they could measure it gradually bumping out. And they decided it's okay, it's the right position, and they kept going, and they were right. So then the secondary mirror pops down. Telescopes usually have at least a primary and secondary mirror. Secondary puts the light down into the instrument, which will have its own optics. In this case, there's actually a tertiary, a third mirror, to help refocus, reshape the image so that it's without distortion. So that pops down to within a millimeter of exactly the right spot. That was within margins. And then the primary mirrors, there are 3 on each side that are folded up like wings. They pop out into position, and now everything is locked in place. Now the next fun part begins. Oh, in the meantime, on the way out, it's time to chill, literally. Literally, you want to have this thing operating as close to absolute zero as you can, but you don't want to do it all at once. So, ironically, the spacecraft that's supposed to be incredibly cold has heaters on board. Those did 2 things. One, they helped drive out any moisture in the air that was inside the instruments. You don't want that freezing up and becoming ice, possibly expanding, breaking things, or literally coating sensors and optics, and now you literally have a foggy view of the universe. So that's the sun side temperature on the top of the graph, and you can see how things chilled on the star side. Also, you don't want to chill things off too fast, because if you do, basically it's like pulling a glass out, a drinking glass out of boiling water and then dropping it into a pot of icy water. It'll shatter. So you don't want the parts to break. Yes?
From the time it started unfolding until it was completely done, took minutes, hours, days?
Week.
Week?
Over a week, yes. And that was just getting things popped out, and the tensioning. Basically, the whole thing, they had plenty of time to do it. It took them a month to get out on station. They launched in January. On December 25, they arrived on station in January 24. So they just took their time doing it. If there had been a delay for some reason, they would have adjusted how they did the burn to get in there. But it was designed to go slow. This is something that requires a lot of patience. Okay, so here we have, there we go. The instruments cooling down. So some of them dropped out very quickly, others were brought down very slowly. That instrument with the white line that bottoms out, I believe, is operating excuse me, at about 7 Kelvin. That's about 14 degrees above absolute zero. And now it's time to get lined up. So you've got everything in place. You have to align those mirrors. First thing they did was release the latches that were holding the mirrors up against the grid. And by the way, the mirrors are gold coated. That is the best material for reflecting infrared light where they're going to be working. It's very thin beryllium alloy made by a company in Cullman, Alabama, which also built the window frames for the space shuttle and the platforms for the inertial guidance system on the Apollo spacecraft. So getting things lined up, and here's a selfie. My computer will. There we go. Here's a selfie taken shortly after they started checking out which way the mirrors pointed. So they had to release the latches, and this was done very slowly. Some of the movements were done at the speed of about 1 millimeter a day. And then run the motors just a little bit and turn them off, turn them off, to let them cool off so that the heat that they produced would not mess up the cool down process that they needed on the mirror segments. So first image, they're looking at a star in Ursa Major, the Great Bear. It's a sun-like star because there's basically nothing around it. So this gives them one really good, stable point source they can look at. And it's just all over the map. The bright spot there, primary mirror selfie, that's not a picture of the star. That's a picture of the mirror illuminated by a star. So they're gradually tweaking these things back and forth, working to get them lined up, and then eventually they do have them lined up. They got the point source centered in each mirror. You get a selfie like that. And again, that is the primary mirror illuminated by one star, and the inverted Y formation you see is the shadow from the struts supporting the secondary mirror out in front. And there's the star in perfect focus. Now, that spider pattern is not part of the star, and you can see this in a lot of star pictures. Sometimes it's a 4-point star, sometimes in this case it's 6-point because we have 3, and just the way the optics work, you get the Y shape upside down and right side up. That is light diffracting off the edges of that support structure. Okay, so why do we want to look in the infrared? Lots of information there. Okay, the one picture of cute fuzzy creatures in the window. Right, meerkats at the zoo, and a freshwater croc. So conventional visible light, what we would see if we went there, and the meerkat and the croc in infrared. So you're looking at their body heat, and also a bit of light reflecting back out their eyes. So the electromagnetic spectrum carries a tremendous amount of information that we simply cannot see with our eyes. As great as our vision is, it's extremely limited. And one comparison I like to make is that it's like going to a symphony, and if you can only hear the middle C key and the key on each side of it on the piano keyboard, you're missing the whole symphony. We can hear and learn a lot in those middle 3 keys, but there's so much more going on. So gamma ray, X-ray, ultraviolet, as I mentioned, different satellites, telescope designs. Hubble Space Telescope just rewrote so many chapters in astronomy and astrophysics, operated from in the near ultraviolet into the near infrared with its last science instruments. Webb is going to cover a broad range of the mid-infrared. Spitzer, the one that we launched in the 1990s, was a little farther out in the infrared, so there's a little bit of overlap among those 3. And then other telescopes look farther out, and when you get into certain parts of the radio spectrum, you can do it from the ground, like the Very Large Array up at Socorro. You have to go to space to do infrared because the atmosphere simply messes things up. Water vapor in particular is very good at absorbing or reflecting infrared, so you simply need to be above the atmosphere to get that. Okay, somewhat complicated graph, but I threw this one in for a couple reasons. One, you can see by the different names, Hubble, Webb, Spitzer, so the different parts of the spectrum, so that's visible over on the left and then going into the far infrared and millimeter wave. ALMA is the Atacama Large Millimeter Array, big cluster of radio telescopes, high Chilean mountain desert. Herschel telescope looked in different parts of the spectrum. So again, this is part, we got a trampoline upstairs? This is part of listening to the entire symphony. And there are two reasons for going with bigger and bigger and bigger telescopes. First off, it gets you a sharper image. Okay, the way the light interferes with itself to form a picture, the wider the telescope, the better, the sharper the interference that you get, so you can make what we consider to be sharper images. And resolution is mathematically just means how close can 2 points of light be and still be seen as 2 points of light instead of just one. The bigger the telescope, the smaller that separation can be, and you can still see it as 2 points of light. Bit of math involved, but basically you get sharper. Also, you see much, much fainter. So you make a telescope 2 times as big as the previous one, you collect 4 times as much light. Make it 3 times bigger, now you're collecting 9 times, goes up by the square. The price does too, by the way. Okay, so among the things that this will let us get, we can see through dust and study dust in deep space. This is what messes up our view of deep space objects, is interstellar dust. So this is the Catchpaw Nebula. 2 images taken by the European Southern Observatory, visible light near infrared, and then a picture taken by Spitzer. And you can see much, much richer detail as compared to what the other 2 can pick up. Infrared is not scattered as much as visible light, and in particular blue light. The sky is blue because light is scattered by aerosols. Shorter the wavelength, the more it's scattered. Okay, now, Spitzer. This is an infrared camera, and almost the same wavelength with Webb in mid-infrared during calibration test. Same patch of sky down in the Magellanic Cloud, which is a little satellite galaxy south of our Milky Way. That's the kind of sharpness we're going to be getting. Okay, one of the things it's going to do is let us look into the ancient universe. Because when the universe expanded after the Big Bang, space itself stretched, and that stretched light coming from distant stars. The more distant the star or the galaxy, the more the light has been stretched literally by the expansion of space. So this is going to let us look deeper, farther back to basically the period of ionization, when the gas was so dense and so hot that light just simply isn't going to penetrate to begin with. Okay, so some of the things we're going to be looking for. So, Big Bang, after that is a period of reionization. Gases get hot, nuclear fusion, and so on. Lots of light, and atoms are now ionized. Free electrons running around. Stars begin forming, they assemble galaxies, and it's all very, very dense and opaque until things start to thin out, until galaxies separate, and now light can travel freely. So it's back to that horizon that Webb is going to take us closer. This will let us seek the first galaxies, the earliest galaxies. In fact, one of the things I like to talk about is having a flip book of galaxies over time, so that we can understand better how they evolved. This goes to the origins. Or the death, dissecting black holes. Yes, you can see black holes, well, actually see the material around them. And it's the universe's worst traffic jam, as material is swirling around, might get swallowed in, and in those last few hours or minutes, seconds, whatever, before it goes over the event horizon and disappears forever, it becomes incredibly hot. So we observe it in gamma rays and X-rays, but also there's a lot to be learned in infrared. Okay, re-examining how stars form, live, die. The pillars of creation, famous Hubble image. At left, you can see lots of dust, invisible light, and in very, very near infrared, it's much clearer. You can see more details. Okay, detecting molecules in star-forming regions. And not just star-forming, but planetary-forming regions. What is the chemical makeup? How much hydrogen? How much helium? How about the other elements that come along with it? One of the inside jokes, geek jokes in astronomy is go into astrophysics because your chemistry classes are a lot easier. You only have to know hydrogen, helium, and metallicity. Everything from heavier than helium, from lithium, beryllium upward, considered to be metallicity. Okay, understanding those ratios helps us understand how the stars are formed. One of the things we don't fully understand about our sun is what's the metallicity on the interior. We can measure the chemical content very effectively on the surface, but we don't know exactly what the metallicity is in the interior, and that affects how fast it burns through its nuclear fuel. Won't make much difference for us in our lifespans, but it's information we'd like to have. It helps us understand things better. And we won't be looking entirely far and away. So these three images on the left was taken by the Gemini Telescope. As the name suggests, there's two identical 8-meter telescopes, one on the big island of Hawaii and one in Chile, just studying the heavens north and south in infrared. So the middle picture, Jupiter, more familiar image for most of us, taken by Hubble, and on the right, Hubble image in near ultraviolet. So on the left, the bright areas that you're seeing are where hot gas is circulating from the interior of Jupiter because it radiates more energy than it gets from the sun. It's hotter inside than it is on the outside, so because of gravitational compression. So this shows us a lot of the gas circulation that's going on in that atmosphere. Look for distant planets. A couple of the instruments on board Webb have little specks of black built into them so they can be used as coronagraphs. So we can look at stars that have been identified as having planets, block out the bright light from the star, and see the planets orbiting them. And possibly get signatures, infrared signatures of the gas composition in their atmospheres. And the one that you really want to find is molecular oxygen. Oxygen reacts with just about everything over the long haul. If a planet has oxygen in its atmosphere, something is producing it, quite possibly life. So that would be great excitement. And just basically, it is kind of a 42 machine. Life, the universe, and everything. Yes, and we're going to wind up rewriting a lot of the answers and coming up with new questions as a result of what Webb will be doing. So the first science image is supposed to be released on July 16. We're supposed to get solar system ambassadors are supposed to get a briefing next week, not in time for this talk, about what to expect in those images. So we've already seen some. Those are considered to be engineering images, and they're deliberately tinted orange, just to remind everybody this is infrared. One of the things that we do with images, in particular down there on the left, that's the nebula, and the galaxies up there. One of the things we like to do with images is we color them. Picasso said that art is a lie that makes us see the truth. Most astronomy images are very artful. Those are colors that Mother Nature never intended, but we tint things. We might assign one color to light emitted by molecular oxygen, a different color to iron, or maybe a different color to an area that's producing gamma rays. Combine them and we get these very colorful pictures that aren't really what the object looks like, but it tells us what's going on. And actually, what really goes on in astronomy, the way astronomers work, people tend to think that that image of Edwin Hubble looking through the finder scope on the 48-inch telescope at Mount Palomar, has got a pi down jacket, he's peering through the finder scope. They think that's how astronomers work. No. John Barentine, who worked at Apache Point, will tell you it's like this. What the heck is that? And then you go in and torture the data until finally you get a graph that matches what your grant proposal said. So that is it. You've just witnessed a miracle. I've done a presentation in half an hour.
Yeah.
This will never happen again. Questions? Yes.
The Hubble Deep Space Field that shows all the galaxies,
Yes, sir.
you're gonna take one of those with the Webb to see the difference?
I'm sure that they will, yes. Now, those of you who might not be familiar with it, the director of the Space Telescope Science Institute and director for Webb has a certain amount of discretionary time. He can assign some of the observatory observing time. If something interesting pops up, they've got 48 hours, for example, that they could reprogram the telescope. Sorry, whatever you're observing will come back to you later, but gamma ray burst or supernova just went off over there and we want to get pictures of it real fast. And some of it is simply not exactly things that would strike his fancy, although that was kind of the feeling at the time. He decided that the Hubble would spend several days. And how many hours actual observing time was it, Tony? A couple hundred?
Couple hundred.
Yeah.
Over weeks.
Yes. Staring at a blank spot in Ursa Major, the Big Bear. And he selected that spot simply because it appeared to be blank. And other astronomers said, you're wasting your time. Telescope time is valuable. It's one of almost as expensive as astronaut time on space station. This is a complete waste. And the picture came back and it was like, bam. Stars, galaxies everywhere. I mean, they knew there was a handful of stars in the field of view, but all these galaxies pop up. And one of the things that we do when we take pictures, old school on the ground, you'd have the telescope pointing at the target for several hours, exposing one film plate. In space, we stare for several hours, but we take dozens, even hundreds of images, because any one of them is going to have radiation noise hits in it. But those will be random. So you stack them up in the computer, and if this pixel is black, 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 bright, not so bright, black, 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 it's a black spot, and that was a radiation hit, so you erase that. If it's almost constantly this level of brightness, and occasionally maybe it drops out completely, that was noise in the system, this is a bright area. So you stack them up, you stack up dozens of images, align them, and sometimes you might be pointed at the target like that, and maybe just shift a little bit off for the next round, just to get a little bit of overlap on the pixels, and that can help sharpen the images just a tad. So that's what Webb will do. I'm sure that they've got the deep field area on their list of things to do. And when that knocked everybody's socks off, they did another one, excuse me, Hubble Ultra Deep Field, and showed even more, and that helped rewrite cosmology.
So what we get from James Webb is really gonna be impressive.
Yes, yes. Oh, and one bit of apples and oranges comparison. So I was talking about bigger telescope gets you sharper images, but at the same time, as you go farther out in wavelength, as the waves of radiation going from X-ray to ultraviolet to visible, and you get out into the infrared and then radio, the images get coarser, they get blurrier as a function of the wavelengths being longer. So as big as Webb is, some of its observations will not be as sharp as Hubble, simply because it's working in a much longer wavelength range. That simple physics, the only way to get around it is give us 100 billion and we'll build an even bigger telescope. And they are thinking about those. It's not fair to say, well, it's not as sharp, therefore we shouldn't have done it. We're looking in a region that we haven't explored before. So as it was with Hubble, when it was launched, every place we look, it's going to be discoveries. Other questions? Yes?
Will this have any, will they try to find Planet 9 at all with Webb?
Okay, Planet 9, body that a number of people believe is roughly an Earth to Neptune sized body orbiting out deep in the solar system. So far, nothing to support that. Doesn't mean it's not there, we just don't have any proof that it is. It's all supposition. It could detect it if it was pointed in the right place at the right time. Because one of the challenges about spotting a body like that is that it's going to be so far out that it's going to be incredibly dim, not much sunlight for it to reflect back to us. And an example is Neptune is 30 times farther away from the sun than Earth is. That means that the light Neptune gets is 900 times fainter, 30 times 30. Then the light that reflects back to us is about 81,000 times fainter, because it's 900, that 1/900th times 1/900th coming back to us. So it's incredibly faint, plus it's going to be incredibly cold. But Webb's designed to look at incredibly cold stuff. Studying the bodies out in the Kuiper belt, trans-Neptunian objects at immense deep freeze around the solar system is one of the science areas that Webb will be exploring. It'll look at Pluto. It'll look at I forget the name of the small body that New Horizons flew by a few years after Pluto. It's an incredibly rich area, and that'll be part of what it explores. Somebody over there, a question? Yes, sir.
What is the life expectancy? I guess it has a nuclear power supply.
No, it does not.
No?
It does not have nuclear power. Life expectancy is was planned as 10 years. It has solar panel that powers it. Not a very big one, but quite efficient. Solar powered. Most of the cooling is passive, but it does have active closed-loop refrigeration cooling on closed-loop refrigeration on the instrument that goes down to 7 degrees, 7 K above absolute zero. That could be one of the things that they might have to replace in a robotic servicing mission if we decide to go that route. The original plan, again, was designed for a 10-year lifetime, but the Ariane rocket did such a good job of putting it on course that meant they didn't have to use as much onboard propellant as they expected to do the mid-course correction and then put themselves into the halo orbit around L2. So right now, nothing breaks down. They're projecting 20 years. And if we rendezvous with it, just attach a propulsion module. I don't know if they'll be able to basically put jumper cables on it with a replacement solar panel. Solar power is brutal on solar panels. The sun just beats the heck out of them. And when you put a solar panel on a satellite, we figure out how long is this, okay, 5-year life, that's how long we want it to operate. How much power do we need at the end of that 5 years? Say 100 watts. You put on something that's producing like maybe 200 or 300 watts at the beginning, simply because sunlight's going to beat it up, and you're hoping that you have 100 still being generated at the end of that time. Now, having it nuclear powered would be a problem, because now you've got a really hot source right there next to the telescope, and you've got to have extra insulation, etc., to cool it off. Plus, the radiation from the plutonium decaying in the RTG, radiothermal isotope generator, like they used to power the science packages on the moon and the New Horizons spacecraft. The radiation from that is going to just flood your instruments with noise. So the astronomy community really doesn't like any idea for nuclear-powered spacecraft or nuclear rocket engines, because they're going to be listening. Their telescopes in orbit will be listening to the noise, basically the radiation coming off of those devices. So yes.
This is on an unrelated note to the Webb telescope, but
It's okay.
what is the probability of a black hole forming out of an exploding star compared to the results of
Okay.
stuff?
So you're worried about one, and black holes are part of what Webb will be studying. So you're worried about black hole forming in the neighborhood?
No, not really. I just want to know the.
Okay, so and I'm not trying to trivialize it. Okay, first off, some people think that our sun, eventually will collapse as a black hole. The probability of that is basically zero. It's not big enough. It'll burn as a yellow star for about another 5 billion years, become a red giant for a short period, then drop out as a white dwarf that gradually fades over the next few trillion years to a black dwarf. None of those exist because the universe just isn't that old. Bigger stars, the odds of them becoming black holes are pretty big. pretty high. And the bigger they are, the better the odds that that's what will happen to them. And what happens is when they explode, material gets blown off, and the stuff down at the core gets compressed so much that it just squeezes out of the universe as we understand it. Laws of physics as we understand them just don't work inside a black hole. Maybe you can figure it out. You do, you get the Nobel Prize in physics. I am not joking. You will get it. Yes?
I was asking about the probability of a star turning into a black hole compared to it just exploding into thousands of times.
Okay, okay, and that's what I was trying to say is, it depends on the mass of the star. The more massive the star, the more likely it is to go supernova. I forget, Tony, what would you correct?
Kretschmer's limit, it's 1.4 times the mass of the sun.
Mhm.
So any star that's that heavy can form a black hole.
Yeah, and there's actually a very neat little narrow region where you get a supernova, but you don't get a black hole, you get a pulsar, which is basically sort of a giant neutron crystal that weighs just about as much as our sun, and it's about 10, 20 miles in diameter, rotates extremely fast, and puts out lots of radio noise, light, X-rays, everything. And some of them are so highly magnetized, it's right at the point of literally frying the fabric of space. Those are called magnetars. But you get much bigger than that. Instead of getting a magnetar or a pulsar, you get a black hole. So the probability really, as Tony was saying, is how heavy is it to begin with. So massive stars live fast, die young, they live pulsating corpse. Yellow-orange stars, red dwarfs, are interstellar couch potatoes, and they last for tens, maybe even hundreds of billions of years. So be a couch potato for long life. Yes?
You had a slide where you said time, something about,
Oh, time to chill?
no, it was, what the heck are we in, solar systems, or what was it? Okay. Galaxies. I think there were galaxies. There were like four or five of them. Was that the same galaxy over time?
Oh,
Or
okay. Oh, the flip
Were
book.
they, yeah, maybe.
Are you talking about the one where they were in a row?
Yeah, they were in a row, and I think there were galaxies.
That one, yeah.
Yeah, is that the same galaxy? Just over time, or are they different critters?
No, those are different critters,
Oh,
but
okay.
but we can trace the evolution. We can start to connect the dots.
Okay. So they all kind of go along that pattern.
Mhm.
Okay.
One of the biggest upsets in recent months is that they found a spiral galaxy, which is the first one there. This was always thought to be the most evolved form of a galaxy, the latest in its evolution. But they found it in the early universe, after a few million years after the Big Bang.
Mhm.
So people are scratching their heads about how galaxies form.
Yeah, it's not supposed to be there. Yes?
I missed the basic bubble on how this thing actually works, this reflector. Are these, you said there was what, 19 mirrors?
18 mirrors.
Okay, are they arranged then in some sort of a spherical shape or a parabolic shape? Or are they in a flat plane?
No, the surface becomes and here I'll go with the, okay, so that's the selfie of the primary mirror. It's segmented. And this is not the first segmented mirror ever built. There are a number of telescopes around the world that are built up from segments because on the one hand, it's easier to manufacture individual segments and then assemble them instead of having a monolithic telescope. 8 meters is about the limit, and that's the casting facility at the University of Arizona. 8 meters is about the limit that you have for a monolithic mirror. The downside is
80?
80.
Oh, 80 meters.
Yes, sir.
Oh, okay.
Okay, so that's about 26 feet. The downside is that when you're polishing a mirror, you can work on the entire surface. When you have segments, each one of those segments is going to have a slightly different prescription than the one to the inside. And getting those optically correct is a bit more of a challenge. So it's a trade-off. Bottom line, the segmented mirrors let you make something really big you wouldn't be able to do otherwise, but you have to pay that price with getting these things manufactured and then getting them aligned. So part of what they're doing is that they've got these actuators that first did coarse alignment, and now they're doing really fine alignments, just final tweaking, so that one way of looking at a telescope, if you will, is it is really just the coating, the reflective coating on the primary mirror, and then the secondary and the tertiary. Everything else is just support structure to hold that coating exactly in place so that it focuses the light the way that you want.
And
So-
one thing, I could probably help you out with this a little
Sure,
bit.
please.
So you have to have all the segments combining their images, right? That gives you one image.
The
But it
mirrors-
only has the resolution of any single segment, right? So what you have to do now is you have to move each one of those segments in and out just a tiny, tiny bit so that all the light that goes to the sensor is in phase. And that's where you get the resolution. So it's not just a matter of pointing these mirrors, but they all have to be at the exact
Same
right
distance.
distance. So all those light waves are marching in phase, or else it'll just cancel itself out.
So these mirrors, though, are perfectly flat.
They're
No,
not,
no, sir.
no, they're all part of a parabolic surface.
They are part.
Yes, sir.
They're all off-axis parabolas.
So once you put these 18 mirrors in, do you put them physically in a singular plane, or are they
You
bent?
put them in the plane of what that
Bent as
curve,
well.
what that curve would be, of that parabolic curve that represents that entire mirror.
You mean you're trying to match them like this?
Yes.
Yes.
So think of it this way: if you had a monolithic 21-foot diameter primary mirror, and it went in with a wonderful diamond saw and then sliced it into hexagons, this is what you would get. But now you have to make sure that they stay in their original positions and they line up.
Oh, okay. And how far, what then is the focal point roughly from the surface of the mirror to the detector, the receiver? What are we talking about for a
Okay, so
distance?
we focus first on the secondary mirror, which is convex hyperboloid. It's bulged outward slightly.
Oh.
That refocuses it onto a third mirror, the tertiary mirror, inside the instrument module, and that directs it. From there, the light gets directed to the different science instruments.
Okay, so you got the 18 mirrors go to a singular mirror, and that then bounces the light back to that hole in the middle of the mirror?
Right.
Okay, and the instrumentation then is back here?
Yes.
Ah, I was wondering, how do you get the data? If you had it
Yeah.
out here, how would you
Yeah.
get it back to Earth?
Yeah. It's called the Cassegrain optical layout.
Okay,
And
that's-
and it's very common in telescopes.
Yeah.
And that's the way you pronounce it? Cassegrain?
Yes.
Not Cassegrain.
Right.
Cassegrain.
Yes.
Very good.
French
Thank
is
you. You've
strong.
answered a ton of questions in 5 minutes.
Yeah, and the data get back to Earth just through telemetry downlink, pointing at the Deep Space Network. So this thing is positioned, I didn't mention this number, it's positioned about just about 1 million miles away from Earth. So we are probably, from that Webb's field of view, Earth is about the same size as the Moon appears to us. But still a significant source of heat, and so is the Moon. So the data come down to the Deep Space Network, just pretty much the same as with other space probes. Yes?
You showed the people in comparison to the actual, yeah, that guy. And it's, so from the diameter of it would be how big? And then from the mirror itself up to the furthest out point, the tippy top, is how far?
I think it's about 40 feet
Oh.
from the primary to the secondary mirror. And really, we're measuring from here, and Tony says this is where I disappear from field of view on the camera. From that point over to that point, diagonally across, that's the 21-foot measurement. So the resolution really is going to be driven, I think, more by once you get into the, I'm going to get the cursor there, the body more towards the middle portion. But still, it's going to be stupendous stuff that we just weren't getting before.
Yeah, it's comparable in size to the biggest telescopes we have right now. They're building bigger ones.
Mhm.
It's comparable to like the Keck and the Gemini and all those telescopes.
Yes, in the back.
One more question about black holes.
Uh-huh.
Would time slow more with a bigger black hole or a smaller? Or is it equal?
And we don't talk about black holes so much in terms of size because the fabric of space and time gets warped. We talk about how massive they are. And for example, the black hole at the center of the galaxy is just millions times the mass of our sun. It just eats stars for breakfast. And yes, time dilates because of the intense gravity. And we know that that happens because just about 50 years ago, NASA launched Gravity Probe A from Wallops Island, Virginia. And it had a very precise hydrogen maser clock. Basically, it was counting how rapidly energized hydrogen atoms would flip back and forth. They built two of them. One they kept on the ground, and one they launched to an altitude of 4,000 miles, basically the radius, the distance from the center of Earth to the surface. So at that distance, Earth's gravitational pull will be 1/4 what it is at the surface. So you're now twice as far from the center of Earth. 2 times 2 is 4, 1/4. Gravity is 1/4 as strong there as it is here. And the clock on the rocket was going a little bit faster because stronger the gravitational field, time starts to dilate, and they were able to measure that distance, that difference. So inside a black hole, yes, things get really, really changed. Actually, let me rephrase. Outside a black hole, it really changes. And we can measure how black holes and pulsars rotating drag the fabric of space-time with them. When you get old enough to see it, they dance to the time warp. So we know that that's happening. But inside, as I was saying, we just don't know. Laws of physics, as we understand them, just break down at that intense gravity. So maybe you can figure it out one day, seriously.
And you wouldn't even get to experience it because anything that goes over the event horizon or by the event horizon stretches out into oblivion.
Yes. Yeah, in fact, what he's saying is it becomes so intense that nuclear particles get stretched and probably shredded from protons and neutrons down to individual quarks. So you're not going to enjoy that ride fried long before you get there.
Now, there's a term that's called spaghettified.
Yes, spaghettification, yes. So, and I think we just ran out of time on your card, Tony.
Yeah, probably.
Okay. So, one more question?
Yes, roughly, do you know what the frequency is that these guys are using to transmit all this data 1 million miles back?
It's probably in KU band.
KU?
Yes, KU band, part of the radio
Which
spectrum.
is like up around 20 or so gigs?
I don't know what the exact frequency is, but it'd be comparable to what's been used by New Horizons, Galileo, Cassini, and other spacecraft. Because the antenna is not that big. The antenna itself is not that big. In fact, let's see. So on this one,
Isn't that the antenna on the bottom there?
yeah, the arrow is just so narrow. There it is.
Yeah, that's smaller than a mirror segment.
Yes, it's smaller than a mirror segment. So that likely is up in KU band.
Thank you.
Okay, well, thank you for coming. I do not know what the subject is. Do you know the July topic? Saturday, not this Saturday, but Saturday next, will be Science Saturday down at Pizza 9, and the activity there for the kids will be talking about how stars form. Okay, so thank you for coming.
Cool.